Hey there, it's our fourth video concerning angular and linear velocity, and I'm working off a worksheet that has that title, 3.3 Linear and Angular Velocity. We'll look at problem number 5 here about a Ferris wheel that has 250 feet in diameter. Hey, first step, we don't use diameter in math, we use radius. So let's change that right away. That's one common mistake we want to avoid. Makes one rotation. That to me sounds like an angle in radians. So one rotation I know is 2 pi radians. And that rotation happens every 45 seconds. That's the time unit. So, I think in these word problems, it's very helpful to kind of write out all the variables and the units, right? We want to be consistent. Part A says find the angular velocity, right? Angular velocity is denoted by the Greek letter omega, which looks a lot like a W. Incidentally, it's lowercase omega, if anybody happens to be a Greek scholar. Uppercase omega has a totally different symbol, and it's used for Ohm's law of resistance if you take physics. I think you'll see that you use a lot of Greek letters as you kind of move on in science and math. And angular velocity is just angle per time, angle per time. So that's theta over t. And so what am I going to do? For theta, what's my angle? It's 2 pi radians, and my time unit is 45 seconds. And check my units. Part A said express my answer in radians per second. That's what I'm given. So all I have to do is throw that into my graphing calculator, and I get 0.14 radians per second. Okay, so that's part A of the problem. And then part B said, hey, get the linear velocity. And of course, linear velocity, we know the formula is r theta over t. But hey, guess what? This theta over t is the same as omega. It's what we just found, right? We just found theta over t, right? So we can just rewrite that as r omega. We could save a step. So of course the radius we have is 125 feet, right? And omega was 0.14 radians per second. And when I multiply, but incidentally, hopefully you kept that 0.14 on your calculator, and because it was more than just 0.14, right? That was just rounded off. And if I multiply this out, I get approximately 17.45 feet per second. One thing I think you should note is like radians, when we go back to linear velocity, we just kind of drop it out. We don't say feet radians per second. I know that seems very weird that we would drop a unit out, but radians are really the 2 pi in the circumference formula for a circle, in the 2 pi r. That's the only purpose it serves, so that's why we drop it out. Okay, I'm going to go one more quick problem here to finish off the worksheet. Again, I'm going to go fast, so feel free to pause your video at any time if you'd like. I got a radius on an SUV of 18 inches, which is totally unrealistic. I think that's kind of small. I could be wrong though. What do I know? The SUV travels at 60 miles per hour. That's a linear velocity. I get 60 miles per hour. And I want to know what's the angular velocity. Remember, that's what omega is. And I want the unit to be radians per second. And I think you'll see the hardest thing is matching up the unit correctly, right? So I do have a formula that ties all three of these various variables, together. Linear velocity is r times omega. And I can just start filling in here, right? My linear velocity is 60 miles per hour. Keep your units because we got to make sure we have the correct units at the end of the problem. My radius is 18 inches, and I want to know, hey, what's the angular velocity, which is omega, which to most of us just looks like a W, right? And so now I want W by itself. Just do some algebra. I said it. I want omega by itself. So omega would be 60 miles per hour. And of course, I got to divide by 18. So 18 inches would also come to the denominator. And what do I got here? Well, I want radians per second. So unfortunately, I have to do a heck of a lot of canceling or dimensional analysis. So actually, I'm going to move this over here, give myself plenty of room. Miles and inches, can I cancel them out? I can. Hopefully you realize that I can get rid of miles. I can actually go to feet. That's 5,280 feet. And that'll cancel out my miles unit. I know a foot is 12 inches. By the way, this problem kind of demonstrates why the metric system is better, right? We're not just moving the decimal, we have all these calculations to perform. Inches automatically cancel out, and I kind of lost my length unit, which is good because I want angular velocity, I want angle per time. Notice I'm shooting for radians per second. My time unit is hours, so we got to get rid of an hour. And an hour I know is 3,600 seconds. I guess you could have gone at 60 minutes in an hour, 60 seconds in a minute. 60 times 60 is 3,600. I guess I skipped a step. Now, if you look at it, I can multiply everything across. So my angular velocity, 60 times 50, 280 times 12, and I'm going to divide by 18 and divide by 3,600. I get about 58.7 radians. Oh, actually, you know what? I get 58.7 nothings per second. This is going to be weird. Everything canceled out on top. You know what we got to throw in? It's the thing that we threw out in the last problem. We got to throw back in the radian unit. I know, kind of weird, guys, but when you're talking about angular velocity, when you're working backwards, you gotta throw radians back in. The thing we usually omit when we talk about linear velocity. Okay, a little bit confusing, but hopefully that was helpful for you, and I'll see everybody in class. All right, take care.